Hello, my name is Serena, and today I will be teaching you how to do number 6 from the Calc BC 2003 FRQ. So basically in the question, they give us a power series, which is defined as -1 to the n, x to the 2n over 2n plus 1 factorial. And part A of the question asks us to find f prime of 0 and f double prime of 0, and it asks us if f has a local min, max, or neither at this point. The first thing we want to do is because they give us our f of x function, and it's asking for f prime of x and f double prime of x, we can express these two functions in terms of the power series that they give us in the question. So basically, using what we know about derivatives, we can find f prime of x. So my approach to this question was to find the derivative of the terms. I personally find that easier for me, but sometimes people will also take the derivative of the actual power series. For example, if you were to take the derivative, it would be n to the 0, infinity. So you wouldn't change any of the n terms, but for the x, like the normal way you take the derivative of an x function, you multiply the exponent and then subtract the exponent on x minus 1. So you could express the chain of polynomials using this. I just find it easier to evaluate the terms that they give us. So by taking the derivative. So if we were to evaluate this at 0, you would see that all of these x terms would have 0 in them, making the entire sum just 0. So that's our f prime of 0. So we can find f double prime of 0 using the same approach as we did in f prime of x. So if we plug in 0 to these terms, they're all going to go to 0. F double prime of 0 is going to be -2/3. To determine if this is a local extrema, we can look at the first and second derivatives. So since the first derivative is equal to 0, we know that the function is probably going to change signs at that point, meaning that it's either a local minimum or a local maximum. But we're not quite sure yet until we check the second derivative. And since the second derivative is a negative number, we have a function that's concave down. So because it's concave down and our first derivative equals 0, we know that this is going to be a local maximum. Because if it's concave down, as we can see, the peak of the graph creates a maximum. So we know there's a local maximum at x equals 0. Next part of the question is asking us to show that 1 minus 1 over 3 factorial approximates the f of 1 with error less than 1 over 100. So we know that this is going to be an error problem, and since the function is alternating series, we know that we can use our alternating series error, which is represented by r of n is less than or equal to a of n plus 1. Since we want our error less than 1 over 100, we can set this less than 1 over 100. So like I mentioned before, the power series that we have, each term in it represents the certain n value or term that we have. So for example, this is our n equals 0 term, n equals 1, n equals 2, and etc. So basically what it's asking, what it means by this formula is it's asking us to find the nth term where once 1 is plugged in, the value is less than 1 over 100. So our error inequality represented by r of n is less than or equal to a of n plus 1 basically means that for whatever term where we plug in 1, which equals something that is less than 1 over 100, we are going to use up to that many terms, excluding the one that was less than 1 over 100, to find the error in our power series. So I'm going to represent that by first plugging in 1 into each one of these terms to see which one is 1 over 100. So we know that this one is simply going to be 1. If we plug in 1 into this one, we're going to get -1 over 3 factorial, which is not less than 1 over 100. If we plug in 1 into this one, we get 1 to the 4th over 5 factorial, which equals 1 over 120, which is less than 1 over 100. So as we can see, this term works. And now that we have this term that we're using, we can basically plug this in into our error inequality. So basically, r of n is less than or equal to a of n plus 1, and in this case our a of n plus 1 is a of 2. So the error is going to be now all the terms up to the term that was less than 1 over 100. So our error is going to include n equals 0 and n equals 1. We know that our r of 1 is going to equal 1 minus x squared over 3 factorial. Again, the 0th term and the first term, all evaluated at x equals 1, and by substitution we can see that this exactly equals what we were trying to prove. 1 minus 1 over 3 factorial. So my approach to these types of error questions is to first determine if it is an alternating series error, to use this formula, and then to plug it into every single term in the power series and determine what value is less than the desired error that you want, and to basically add all the terms before that. What a lot of people tend to forget is to exclude the term that was less than the desired error, but just remember that you have to exclude this number and add up all the terms before to find the correct error. Part C, which is the last part of this FRQ, is to show that y equals f of x is a solution to the differential equation xy prime plus y equals cosine of x. So the first step I would approach is to look at our differential equation, and it might be a bit deceiving because one's first instinct might tell them to integrate this equation, but it looks very difficult to integrate. So it might help just to find the sum of these terms and just to determine that equals cosine of x. So we're going to do that by looking at each single variable individually. So what I want to look at first is what y prime is equal to. So we have our f of x, and to find f prime of x, or y prime, we can just find the derivative of each of the terms in the sequence. So we have our f prime of x, now that we have our y prime, we can multiply every term by x. So our xy prime. So our last and final step is to add r of y to our xy prime expression. So this might be a bit difficult looking at first, only because we have so many different terms and one would assume that we have to do common denominators and stuff, but looking at the two terms, we can see that almost all of the terms that have the similar exponent on the x also have the same denominator, so we don't really need to do common denominator. We can simply cancel out the terms by subtracting the numerators. So from here I'm going to add the terms from xy prime to each term of f of x to get our xy prime plus y. As you've noticed by now, I haven't really simplified my factorials in the denominator, only because I didn't want to complicate my process in the beginning. I'm going to cancel out the factorials with the numerator. So now that we have our final chain of polynomials, we know that cosine of x, its power series, is represented as from n equals 0 to infinity of negative 1 to the n, x to the 2n over 2n factorial. So looking at each term in this sequence, we can see that it aligns directly with our cosine of x function. For example, if we plug in 0, we're going to get 1. If we plug in n equals 1, we're going to get negative x squared over 2 factorial, and we have just proven that these two series are similar without the troubles of going through integration and just using basic knowledge of derivatives. So in my opinion, power series and error questions on AP tests are generally the more difficult questions that are on there. So I put up a couple of different FRQs that are great resources to practice power series and basically the applications of them. And one thing that I noticed is most of these questions were the last on the AP test, number 6. And this is helpful to keep in mind only because you know what to expect on most of these AP tests. And if you think that you're not going to get a power series problem, it's usually at the end. So I wouldn't get too excited if you're on question 5 and you still haven't noticed a power series question because it's probably going to be the last one. So these questions are a great way to strengthen your knowledge on the power series questions, and I put another link to Khan Academy, which does a great job in explaining power series and its applications. Thank you so much for watching my video, and I hope you learn a little more about power series.